Okay, so yesterday we started a new chapter about eigenvalues and eigenvectors. We started the discussion with linear transformations, okay, between like on a vector space, from a vector space to itself. Then we defined something called eigenvector and something called eigenvalue, and these were defined by if L sends the vector to a multiple of that vector, okay? Here, this lambda is a scalar, but in this case, so up until now, we always assumed that scalars were real numbers, but now we make a change and we must allow complex numbers to be scalars as well, okay? So if L sends a vector to a multiple of itself and that vector is not the zero vector, then that vector is called an eigenvector, and that scalar is called an eigenvalue of the linear transformation L. Okay, so this is like a L. So an eigenvector is a vector for which L is just basically multiplying it by a scalar. Okay, so this is an eigenvector. So if I apply, so this is the red one is X, and the orange one is L of X. Okay, so if we can find such a vector, then we call it an eigenvalue, an eigenvector. Of course, this picture is somewhat misleading because lambda can also be a complex number, and in that case, this is basically some kind of rotation, okay? But don't mind that. So we will basically be concerned with linear operators which are basically matrices, okay? So this is sufficient for our treatment. In fact, if L is not a matrix, then L has a matrix representation, and we did an example about this, so that everything which is true for the eigenvalue and eigenvector of L is true for that matrix representation. Okay, so here we're not making a huge I mean, we can still discuss eigenvalues and eigenvectors, and we don't lose like in generality. Okay, so for example, we started with this example, a 2 by 2 matrix. Okay, we have seen a method to compute to compute eigenvalues and eigenvectors, and the method leads to a general thing, which is given any matrix, we can define a polynomial which is the determinant of lambda times identity matrix minus the matrix that we are looking at. Okay, so if I take this determinant, the result will be a polynomial in the in lambda. Okay, so now the eigenvalues are basically roots of this characteristic equation. Any lambda which solves this equation is an eigenvalue. Okay, then we applied this to a 3 by 3 case. In this case, okay, so we find the characteristic we find the characteristic polynomial where is it? Okay, we find the characteristic polynomial which is a degree 3 polynomial, okay, cubic polynomial. This is normal because if I take this determinant, in general, if this is an n by n matrix, the result will be a polynomial in degree n, okay? So the roots of the characteristic polynomial are the eigenvalues of the matrix. That's good. So if we go back to this example, so we have this polynomial. Now, how can we find the roots? Of course, for cubic polynomials or any polynomial, so there's an important theorem in mathematics which says that you can find the exact you can find an exact formula for the roots of quadratic polynomials, which are polynomials of degree 2, okay, which we all know, okay, so we know how to solve like the solution of this, right? So we know the solution for this. So we know this, we learned this in high school, minus b delta over 2a, right? So there's a similar formula for cubic polynomials. And there's also a formula for quadratic polynomials, like polynomials of degree 4. So there are formulas for these ones, but the formulas are not very useful. So they are very long and not very useful. So, and there's an important theorem in mathematics which says that there is no formula for polynomials of degree greater than 4, okay? There is no general formula. Of course, we can solve the roots of some polynomials, but there is no general formula like this one, okay? So like for a polynomial like this, either we use some numerical algorithms to solve the roots, or what we can do is we can do some inspection. For example, for this one, we know the product of roots is basically 6. So if we look for integer solutions for inspecting, we can see that lambda equals 1 is basically satisfies uh, uh, lambda equals 1 basically satisfies this equation. And then what do we do? Then we can factorize this and we can solve it, blah, 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 and we get the eigenvalues. Okay, we obtain 3 eigenvalues in this case. And then we, for each eigenvalue, we look for the eigenvectors. And here we only did the case for lambda equals 1, and we obtained the eigenvector. So important thing about the eigenvectors is once you obtain one of so you see any multiple of this vector is still an eigenvector. So eigenvector is not a unique vector, okay? So for lambda equals 1, we get this eigenvector, meaning what? Any multiple of this, of course, multiples other than 0 is still an eigenvector. So I left these as an homework, and we looked at another example. In this case, the characteristic polynomial is something like this, lambda squared plus 1. Now, this polynomial has no real roots, okay? Lambda squared is never minus 1 for any real numbers. But we have to look for complex roots as well, okay? So complex eigenvalues play an important role. So in this case, we get these two roots, which is minus I and plus I. And then if we look for the eigenvectors, we can solve for the eigenvectors, and we get infinitely many eigenvectors for each eigenvalue, okay? And something like this. Okay, so today we don't have, so for next week, I plan to solve some general examples about what we covered so far. So this will be the last new topic we will see. So today I'm going to talk a little bit about section 7.2, okay? Section 7.2, which is about diagonalization. Let me see the title. Diagonalization, yes. Diagonalization. Okay, so what is diagonalization? So suppose we have two eigenvalues. Okay, let's suppose we have a 2 by 2 matrix. Okay, so start with a simple example. Let's start with a 2 by 2 matrix, and suppose we have two eigenvalues of this matrix. And the second one, okay, lambda 1. And the second one is A times V2 equals lambda 2 times V2. Okay, so here we're assuming that lambda 1 is not the same as lambda 2. Okay, so this part is important. Okay, let's see. Now, suppose we have a matrix P whose first column is the vector 1, first eigenvectors. Okay, so let's say that V1 and V2 are eigenvectors. So what is the size of this matrix? So the first column is a vector of size 2. So this is 2 by 2 matrix, right? This is a 2 by 2 matrix. Now, let's see what happens if I take this product, A times P. Can I multiply these two matrices? So this is a 2 by 2 matrix and P is a 2 by 2 matrix. Yes, I can do that. And what is the result? What does the result look like? So let me write the matrix P again. So what is this? This is, so there's an easy way of taking this product. Probably I haven't done this in the class, but if you take the product, you see that it's basically the first column is A times the first vector, the second column is A times the second vector. This is nothing related to eigenvectors. This is this kind of product is true for any matrix multiplication, okay? I did this once, maybe in the beginning of the semester, and then I never used it, but it's the first time it shows up here. So if you don't believe me, just try it for yourself, right? Let's do it here. Let's do it. Let's prove this. So if A is this matrix, A1, let me call A, B, C, D, okay? And so here I have x1, x2, and let's say y1, y2. So what is my claim? My claim is this. So this is basically this ABCD times, maybe this is too old. ABCD times x1, x2. And the second column is ABCD y1, y2. Is this true, guys? What do you think? So if you look at the first column of this one, what is the first column? What is the first column of this guy? So it is AX1 plus BX2 and then CX1 plus DX2. What is the first column of right-hand side? What do you think? So it is AX1 plus BX2. Same thing, right? It's the same thing. So first column of this guy is also the same. So this shows that the first columns of both sides are equal, and you can check the second columns are also equal. Okay, this is kind of proof. Okay, so, but we know that, let's go back here. So we were at this step. So, but we know that AV1 is what? AV1 is basically lambda 1 times V1. And what is AV2? This is lambda 2 times V2, okay? Because we assumed them here. These were eigenvectors. Okay, guys, now another trick, second trick. Second trick is this one. This matrix is basically equal to this product, V1, V2 vector multiplied by lambda 1, 0, 0, lambda 2, okay? So again, this is something that you can prove, okay? You can prove that these two are same. So I leave it to you, it's just checking. Prove. Any questions here? Okay, we're going very good. So let's see what we obtain. So we obtain that this is P, and this is lambda 1, 0, 0, lambda 2. Okay, so what happened? What happened? Okay, so what did we do? So if the matrix P is invertible, if P inverse exists, then what do we get? We get this thing, P inverse A P equals a diagonal matrix, right? This is a special matrix, which is a diagonal matrix. Okay, this matrix is special. This is a diagonal matrix. Is this okay? Very good. This is a diagonal matrix. Now, what is the use for this? Well, one use is this. One use is, for example, if I want to, so this is diagonal matrix. So let's give the name D to it, okay? So this shows that P inverse AP equals D, or I can write this as A equals, okay, let me do it slowly. So P inverse A times P equals D, if and only if. This means that if I take, if I multiply both sides with P from left, what do I get? P inverse A P equals PD. Okay, and this part is gone because this is identity, right? Let me use different color. So this is identity matrix. Maybe I should use this color. Okay, so this is identity matrix. And then what do I get? And if I carry on one more time, what do I get? If I now AP equals AP times P inverse equals PD P inverse. I'm taking product from right, and in this time I get that A is what? PD P inverse. Okay. So this is important. Now let's see what are some why is this useful? Why is this useful? This is useful because suppose I'm trying to compute a square. What is a square? Now I can, so a square means a times a, right? So this is what a square means. So now let's use this notation, this representation. So a is PDP inverse, right? So I'm multiplying with PDP inverse, PDP inverse. Okay, now we know that for matrix product, the parentheses have no importance. You can ignore the parentheses. So if you ignore the parentheses, what do you get? So you get a P times P inverse times P here, which is identity. Okay, so that part is gone. So what do you have? P times D times D times P inverse, which is basically P D square P inverse. What about a cube, or what about a to the power n? If I compute a to the power n, what will the result be? The result will be simply p times d to the power n, p to the minus 1. Okay? So, in general, taking powers of a matrix is not easy, but taking powers of a diagonal matrix is easy. So this part is hard. Let me use this color with this one. So taking this is hard, But this is easy. Okay, one is hard, one is easy. Why is d to the power n easy? So let me try to compute d to the d square. What is d square? So this is lambda 1. So if you remember d, this is lambda 1, lambda 2, lambda 1, 0, 0, lambda 2. So if I compute this, you will see immediately that the result is very easy to compute. This is lambda 1 squared, 0, 0, lambda 2 squared. And if you want to compute d to the power n, basically you're just computing the nth power of the diagonal elements. So this is 0, 0, lambda 2 to the power n. Okay, so d to the power n is very easy. But this part was hard. So if I can use this, if I know that uh, I can diagonalize this, then finding the powers of the matrix is very easy. So, but why is finding the powers of a matrix important? Here, I'm gonna cheat a little bit. Okay, so these are some ideas that that will come up in the future for you, not right now. But we can. I'm hoping that you're taking calculus too. Now we can define something e to the power matrix, a square matrix. Okay. Okay. So this is the usual exponential function, but this time it's not e to the power some number, but e to the power some matrix. So how do we define this? So definition is basically an infinite series that you are seeing in calculus. So if you remember the definition of the Taylor series for e to the power x, you will remember that this is basically a to the power n divided by m factorial. Now this is where a to the power comes, right? So you can not just e to the power a, but you can compute any function of a matrix. So you can define functions of matrices, which are very handy, which are very useful. Okay, so this is one place where a to the n is showing up. Okay, so why is e to the power a important? Okay, why is e to the power a important? Well, we know something. We know what? So calculus 1, so you have taken this class from me. Calculus 1 says if I take the derivative of e to the power ax, this is a times e to the power ax. Now advanced linear algebra says that d to the power dt of e to the power a times t, here a is a matrix, is still a times e to the power at. Okay, so what does this mean? This means something for differential equations. So differential equations, you can write differential equations for vector systems, okay? So here x is a time-dependent vector, and suppose that it's a linear system. So, and A is a constant n by n matrix, and you're trying to find the solution, okay? I think you have, did you take differential equations? Are you taking differential equations? No, that's fine. So that's fine. So suppose you're trying to solve this system. This system shows up in many places, okay? and you're given an initial value for this. And if you can compute the exponential matrix, bam, you get the solution. The solution is basically exponential matrix times this initial vector. This gives you the solution, okay? So this part is the initial value problem. Initial value problem. And bam, you get the solution, okay? So exponential matrix is very, very useful. So this kind of equations show up in all mathematical physics, like biology, economics, computer science, in all the applications, okay? So they appear in a lot of places, so you get the solution immediately. What am I gonna say? So for now, of course, these are just optional, okay? So this part is, I won't be asking you about these in the exams. Okay, so this is just optional stuff. Let me write it here. So optional. Okay. I think I didn't write it right. Optional, right? Anyway, so finding diagonalizing matrix is important. So there's one step here that which we went through very fast, and that step was this part. This part was the important step. So if P inverse exists, okay, so if P inverse does not exist, then I cannot multiply by P inverse, and I cannot find this diagonal matrix. So that's the important part. So when does, so P is this matrix. So when does, let me write here. So the question now is, when does P inverse exist? Okay, P inverse exists. So I will just give the answer without any proof, okay? It exists if V1 and V2 are eigenvectors of distinct eigenvalues. Just as we considered, okay? Okay, now let's look at some examples. Any questions, guys? Dün bir makale okuyordum arkadaşlar. Birisi sorusu olan var mı diye sorunca her zaman bir soru soracakmışsınız. Öyle diyor. Ne zaman birisi sorunuz var mı derse hemen bir soru yapıştıracaksınız. Bu bir hayat şeyi, taktiği. Mars'ın neresindesiniz hocam? Çok güzel bir soru Mustafa Yener. Mars'ın içindenim ben. Okay. So examples. Okay, let's look at an example. Okay, let's take a matrix, which is the matrix 1, -2, and 1, 4. So I think we did this example. Let's go back. 1 minus 1, 2, 4. So yeah, this one, right? So we found the eigenvectors and eigenvalues. So for lambda equals 2, we get this eigenvector. For lambda equals 3, we get this eigenvector. So let's copy them. Oops. So previously, we found lambda 1 is an eigenvalue, which is 2 with eigenvector. So we can take any of those infinite eigenvectors. So it is, we can take 1, 1. Okay, so if you remember, the eigenvectors were R, R, and we're just taking 1, 1. Okay, so R equals 1. And another pair of eigenvalues and eigenvectors was lambda 2 equals 3, and V2 is what? It is 1 and 2. Okay, so what does this give us? This gives us, so the question is A diagonalizable? So I think we didn't define what diagonalizable means. Diagonalizable. If so, find P and D such that A equals P D P inverse. Okay. So here D is a diagonal matrix. So let me write diagonal matrix. And in the light of previous discussion, the answer is yes, because there are two eigenvectors with there are two eigenvalues, and so we can find an eigenvector for each one. So according to this answer here, the answer is yes. Okay, so this gives us what? This gives us this. So what does it give us, guys? So A equals what? A equals this matrix 1, 1, 1, 2, okay, times the diagonal is 2 and 3, 0, 0, and then the inverse of this guy. The inverse of this guy, okay? So there is a little bit of checking. Should we check this? Let's check it, okay? Let's check, verify the answer. So what is the inverse of this guy? So I want you to write, be able to write the inverse of 2 by 2 matrix from like a memory. So this is 1 over determinant, 1 times 2 minus 1 times 1 times, and then what do? We exchange these, we swap these two entries, okay, diagonal entries, and these ones come with a minus sign. Okay, so if we do this, this is 1, and we get this one, right? 2 minus 1 minus 1, 1. This is P inverse. Okay, so I think yeah, so I leave it to you, okay? So it will take too much time. Sorry, I cannot check it here. So homework, check it. Check this. Okay, so here there's a little bit, there's not little bit, there's an important relationship with the independent, linearly independent vectors and this topic, okay? So that relation is this. So suppose, let's write this as a theorem. So if A is an, suppose it's an n by n matrix, and suppose we have a v1 equals lambda 1 times v1. So lambda 1 is an, let me say this. So suppose v1 vk are eigenvectors belonging to distinct eigenvalues, okay? Distinct eigenvalues. So v1 is an distinct eigenvalues. So what do I mean? So v1 is an eigenvector of lambda 1, v2 is an eigenvector of lambda 2, and so on and so forth, and none of these lambdas are equal. Lambda 1 is not the same as lambda 2, lambda 3, so all of them are distinct. In this case, then these vectors are linearly independent. Okay, so this is not hard to prove. It's easy to prove, and you can check it from your book or your internet. Doesn't matter. So this is the first thing. The second thing is this is the first part. Second part. So let's say this is the first part, part A, and the second part is this: if A has n distinct eigenvalues, then A is diagonalizable. By the way, we didn't define diagonalizable, right? Let's go back. Let's go back and define diagonalizable here. Okay, so let's define diagonalizable here. Definition. So suppose A is an n by n matrix. If P inverse exists and D is diagonal matrix, and A is P D P inverse, then A is called diagonalizable. Diagonalizable. Let's use this color. Diagonalizable. Köşegenleştirilebilir demek arkadaşlar. So let's use this as a side note, okay? So this is the definition of being diagonalizable. So this theorem is saying that if we can find n distinct eigenvalues for an n by n matrix, then that matrix is diagonalizable. Okay, so in the previous example, this matrix was diagonalizable because it has two distinct eigenvalues. This is a 2 by 2 matrix and it has two distinct eigenvalues. So as a last example, not the last example, but let's say part C for this one. Where is it? Okay. Okay, let's go here. So part C, if A has, in fact, n linearly independent eigenvectors, then A is diagonalizable. Okay, so what is the distinction between part B and part C? In part B, we said if A has n distinct eigenvalues, then A is diagonalizable. Part C is says if n has n linearly independent eigenvectors, then A is diagonalizable. And by the way, this is not just if, this is if and only if. So I should really write this as this. So I erase this if part. So what I should say is, so there's a distinction between if and only if, right? So I should really write if and only if. So okay. So last 5 minutes, guys. We don't have too much time. So we in part A, what did we see? In part A, we have seen that the set of eigenvectors belonging to distinct eigenvalues, like different eigenvalues, are linearly independent. Okay, so if n has n distinct eigenvalues, that means each one will have an eigenvector and the set of those eigenvectors will be linearly independent. So part B is a special case of part C. Okay, so part B is a special case of part C. So part C is the most general case. So if we can find n linearly independent eigenvectors, then it is diagonalizable. If we cannot, then A is not diagonalizable. Okay, so that's the difference between these two. So let's look at this final example. So suppose we have the matrix, which is 2 by 2 matrix, 1, 0, and 1, 1. So the question is A diagonalizable? So we only need to find the eigenvectors. If we can find more than one linearly independent eigenvector, the answer is yes. Otherwise, the answer is no. So let's check the eigenvectors. Okay, so what do we do? So we first look at the characteristic polynomial, right? P lambda, which is determinant lambda I minus A. So what is this? Determinant of lambda I minus A. What does it give us? So this is lambda minus 1, 0, lambda minus 1. So what is this? This is lambda minus 1 square. This is the characteristic polynomial, remember? And the roots of this polynomial are eigenvalues. So we have only one eigenvalue. So if we could find another eigenvalue, then we were sure that this matrix is diagonalizable. But right now we're not sure. This matrix can be diagonalizable or cannot be. I mean, both possibilities are in the air right now. So which is the case here? Which one is true? Is it true that A is diagonalizable or not? So to see that, we have to look for the eigenvectors. If we can only find one linearly independent eigenvector, then this is not diagonalizable. If we can find two linearly independent eigenvectors, this is diagonalizable. Okay, let's check it. Let's check it. So let's try to find the eigenvectors. Okay, so how do we find the eigenvectors? So what are we doing? In this case, we are looking for the solutions of this guy. So instead of lambda, I put 1. So this is 1. So let me write lambda here, right? So lambda, no. Let's write lambda minus 1. Minus 1, 0, lambda minus 1. Now I erase these lambda and I put the value lambda equals 1 because that's the only eigenvalue, okay? And I'm looking for the solutions x1 and x2 such that this is 0, 0. So these are the eigenvectors. So what does it give me? The first equation gives me minus x2 equals 0. And the second line gives me 0 equals 0. So this only gives me one relation, which is x2 is 0. But x1 can be anything. It can be anything. So the eigenvectors are in this form, x1, x2, so that this is really r times 1, 0. Okay, guys. Now, at the end, what we find is this eigenvalue has only one linearly independent eigenvector, okay? So let's write it. If only one independent eigenvector, then this matrix is not diagonalizable. So the answer is not diagonalizable. Köşegenleştirilemez. Köşegenleştirilemez. Yes. So that's the end of the topic. So we went a little bit fast. I suggest you read the section 7.2. So next week we will solve some general examples related to like the exams, okay? If you have any questions, please ask. Otherwise, we will finish here.